Good morning, good afternoon, good evening, good night. So this is the last parts of exercise number 4, slide 22, lecture set 7. So I will go over what we covered in class. First, the problem is given some information about the theoretical spring constant of type 3 springs. At the 5% significance level, is there evidence that the long run mean for type 3 springs is less than 2.63? Use the summary statistics from a simple random sample given in the following table. So we have a sample size of 50, we have a sample mean of 2.58, and we have a sample standard deviation of 0.064. We want to test if the long run mean is less than 2.63. So we start with our assumptions. So the first assumption is, do we have a simple random sample? Which we do because the problem tells us it's a simple random sample. The second assumption I've written as the normality of X bar, and we can check this off because we have more than 30 observations, so we're able to apply the CLT. The third assumption is that sigma is known, and this cannot be checked off here because we have the sample standard deviation, not the population standard deviation. So this is why we're using a t-test. So on step 3, you can see we have a t-value rather than a z-based test like we did in exercise number 1 from this lecture set. So our null hypothesis is that the population mean mu equals 2.63 against the alternative that the mean is less than 2.63. So again, the alternative hypothesis reflects the question. On step 2, we state our significance level, which is 0.05 or 5%. And on step 3, we compute our test statistic, which as you can see is a t value, which is x bar minus the hypothesized mean divided by s over the square root of n. When we plug in, we end up with negative 5.52. Okay, so we work through the critical value approach, and you can see we have a lower tail test. So I started by sketching the curve. Then I marked down where the critical value is, which is this black marker next to the red shaded area. Then I shaded in the area and labeled that size 0.05. So this is the information that we have from the problem. So the alternative tells us that our rejection region is in the lower tail and the size of it is the significance level. Then we found our t value or the critical value. So we have a t at 0.05 and 49 degrees of freedom because there are 50 observations and 50 minus 1 is 49. So we went to the t table, 49, matched that to 0.05, and we have 1.667. So this is why we have the negative 1.677, sorry. And then we mark down the test statistic, which I wrote in green. This value, negative 5.52, is less than negative 1.677, so it's in the rejection region. So this means on step 5, we can reject the null. All right, now, if we take the p-value approach, right? Okay, so again, we start by sketching. So here's my sketch. Okay, now I'm going to mark down the test statistic. And I'm going to shade the area below the test statistic. So I'm shading the area below the test statistic because it's a lower tail test, because in the alternative, we have the less than sign. So here, the p-value is the probability that t is less than negative 5.52. Okay. Okay. Right, so that green shaded portion here, this is the p-value for this test, which is precisely the probability that t is less than negative 5.52. Now, to figure this value out, what we have to do is basically say any lower tail area with the T curve is equivalent to the upper tail area. So we can say, um, for example, note the probability that T is less than negative 5.52 is equivalent to the probability that T is greater than 5.52. I'm just going to move this down so I have enough space. Okay. And that's just due to the symmetry of the curve. So what this allows us to do is just treat this problem like an upper tail problem. So we can use the t-table to find the area or the p-value as if it was an upper tail curve, as if it was an upper tail problem, and then just translate it to the lower tail case. So we go back to our t-table. We have 49 degrees of freedom, right? So same calculation. And what we're going to do is work our way across the line and look for positive 5.52, right? So we're treating this as if it's upper tail. All right, so we have 1.299, we're bigger than that. 1.677, we're bigger than that. 2.01, we're bigger than that. 2.405, we're bigger than that. 2.68. So we're bigger than this. So our value is over here somewhere. So we are to the right of 2.68. So what that means, because we are bigger than the largest value listed on the line, if we scroll up to the top, we're going to take this area here, 0.005, and we're going to say that the p-value must be less than 0.005. So when we get to the edge of the table, if we are larger than a value listed in the last column, it means that our tail area is smaller than the 0.005. So here we can say, since the probability that T is greater than 5.52 is less than 0.005, then the p-value is less than 0.005. Okay, so then this is our p-value for this problem. Okay. So then when we move to step 5, if we use the critical value approach, we can say reject H0, right? Now it's fine to just write reject H0. And the reason that we're allowed to reject here is because the test statistic is inside the rejection region. Okay, so just for clarity, I'll write since test statistic is in rejection region, right? And then if we take the p-value approach, it would be the same conclusion. We would reject H0, but now it would be because the p-value is less than alpha, right? So remember, the rule is if the p-value is less than or equal to alpha, we can reject. If the p-value is greater than alpha, we do not reject. So then on step 6, we can say at the 5% significance level, the data suggest that the long run mean of type 3 springs is less than 2.63. So we have, as I mentioned in class, at the 5% significance level, so the first part is always just stating the significance level you're at. The data suggest, and then we interpret the mean so that the long run mean of type 3 springs, that's what we're measuring, is less than 2.63. So state the alternative. So the conclusion of the test is always written in terms of the alternative hypothesis. So here we're less than 2.63. Here we have evidence that we're less than 2.63. All right, and that is the hypothesis test. So on the last slide, I'm just giving a summary of the steps of the test. Again, if sigma is known, that's what makes it a Z-based test or the Z-based interval. If sigma is unknown, that's when we use the T-based test or the T-based interval. One other thing that I wanted to point out was, and I discussed this at the start of class, there's a relationship between a confidence interval and a hypothesis test, particularly when they are set up in the same way. So please review the online exercises number 7 and number 8. In particular, exercise number 8 will be very good for preparing for assignment number 4 because this mimics effectively what questions 3 and 4 are like on that assignment. And this goes over the interpretation between or the relationship and how we can discuss the result from a confidence interval matching the result from a hypothesis test.